What's up guys, my name is Gabe and this is Games with Gabe, and this is the next episode in the Coding a 2D Physics Engine in Java series. Now, you should be seeing exactly what we're going to be doing today on the screen right now. What we're going to be doing is creating gravity. Specifically, what we're going to be doing is applying some laws of physics to our physics engine in order to implement our force generators, all right? So we're going to be acting on particles right now. Those two big boxes you saw are actually particles, but we will see why. And that's another thing I should note, is that overall, our physics engine is going to act like a particle physics engine. Even though we will be using full rigid bodies, we will be treating those bodies as a collection of particles, which is kind of confusing, but we'll see that a little bit more once we get into rigid body physics. Now, for particle physics, all we have to worry about is this thing right here. We call this D'Alembert's principle. I probably butchered that name, but that is what it's called. And this I got from the Game Physics Engine Development book. So basically what this says is that the force acting on an object, the resultant force acting on an object, is equal to the sum of all the forces for particles. Okay, so this basically means that if we have some particle in space and it has a force acting at this way, and a small one this way, then the resultant force, we can see this is big, this is a little bit smaller, this is a little bit smaller, would probably end up looking something like, let's change this to red, something like this, right? And so this is the resultant force, and this is useful to us because what this tells us is that if we have multiple forces acting on an object, we don't have to worry about each one individually. Rather, what we can do is we can treat it all as one big force going this way, or in this case, not such a big force. And this makes our physics engine loads simpler, because instead of having to do like, okay, apply this force, figure out what that did, where it placed it, then apply this force, then apply this force, we can just apply this resultant force and be done with it. So what this looks like in our code will basically just be that, say we have a particle and we have gravity acting on it this way, and we have drag acting on it this way, then the resultant force, F, would just be equal to G plus drag. And in our case, this is just going to be two vectors. So this would be a vector 2. We just add each component. So we would do like x1, y1 plus x2, y2 equals our resultant force, which is also going to be a vector 2. It's really simple. There is nothing too complicated about this. It's literally just vector addition. But like I said before, it gives us some pretty profound results. Now, the second thing we want to worry about is Newton's second law. Newton's second law states that the sum of the forces acting on an object equals mass times acceleration. What this implies is that acceleration is equal to the sum of the forces acting on an object times the inverse mass. Okay? Let me say that one more time. The acceleration acting on an object is equal to the sum of the forces acting on that object times the inverse mass. So this is actually exactly what we need for our object, because when we are updating our objects, what we need to do is figure out what the acceleration is. And just remember, the acceleration is basically just the position, how it's moving over time. So if we have a constant acceleration that looks like this, and then we have, so this is A, its velocity then would be increasing, right? Because if its acceleration is constantly going up, that means that our velocity is actually going like this, because at first it's slow, then it increases, so then it becomes exponential, which then tells us that our position is going very exponential, and it's just skyrocketing because the velocity determines how the position is moving over time, right? And so this would be time, the x-axis would be time in all these cases, and then the y-axis would be, in this case, acceleration, velocity, then position. And so this just sort of gives us a visual of how these things are affecting our object in real space. And why is this all important? Because the actual thing that we want to figure out is, what is our position? What is the position of the game object? Because that's what we need to know. Depending on all the forces acting on it, what is our final position, so that we can then set the correct position in our game world and have it look correct as if it was modeled by actual physical forces. So once again, acceleration is the first step to solving that position. So we say acceleration is just the sum of the forces times the inverse mass, which gives us the acceleration acting on that object in this particular frame of our game. And like I said before, acceleration is just velocity per delta time. Literally, it's dv over dt. This is calculus, but we don't have to worry about that because it becomes really complicated if you want to solve the position in instantaneous physics, right? So if you want to figure out what the position is at a particular instant in time, it becomes very complicated because you have to use calculus and everything to figure all that stuff out. But we are on a fixed update time basis. We're basically doing incremental physics. We know what the position of the object was at frame 0. We want to figure out what it was at frame 1, and we know that between this time we have had 1/60th of a second pass. So we already know what delta time is. So that just tells us that our velocity, if we multiply delta time up, is just acceleration times delta time. Pretty cool. So now we know what the velocity of the object is at frame 1. Now to find the position, once again, velocity is just position over delta time. Since we know delta time, we don't have to do the complicated calculus again, right? Because we don't need to figure out the instantaneous position. We just need to know what the position did from frame 0 to frame 1. And so we just multiply the delta time up. Position is just velocity times delta time. Okay? So from Newton's second law, we can garner these equations. We get acceleration from the forces in the inverse mass, velocity from the acceleration times delta time, and position from velocity times delta time. And then we can use this position in frame 1 to update our game object and place it in the correct position in the world. Using all this, let's actually code it and make it happen in our game world. I am inside our project over here, and what is our first step? Well, our first step is, if you are following along with the game engine series, we actually want to disable our docking and IM GUI because otherwise we will not be able to see anything. So just go to the window class real quick, and if you're not, feel free to just skip this real quick so that you can get to the good physics stuff. I'm just going to comment this out, and then I am going to go into level editor scene, and we are just going to remove our grid lines so we can see stuff a little bit more clearly. And while we're at it, let's just remove that stuff real quickly, and we will remove that and that. And that should be good. So if you run this, if you just want to double check and make sure that you are good, you should get no errors, and then you should just get a white screen, which is exactly what we're looking for. Okay, now what is the actual first step? So the first step that we're going to do is we are going to create our physics system. And this is just awesome. This is the moment you have all been waiting for. The physics system is sort of the brains behind our whole physics engine, and this is what's going to drive everything. And so just in case you're wondering, I did add him to the root of our physics 2D package. Now, he is in charge of doing everything. So what is he going to specifically do? And I just realized that I am running this in non-presentation mode. So let me change that real quick so that you guys can see this much easier. All right, now moving on, let's go. And what is the physics system do? Well, he needs a few variables. Particularly, he's going to have a force registry, and this is just going to be sort of the container for all the different forces acting all of our objects, completely abstracted away so we don't have to worry about that. Next, he is also going to contain a rigid body 2D, and this is going to be a list of rigid bodies that are being updated by this physics system. And I keep referring to it as a he. It's just a thing. It is what it is. It is not a person. So I will quit anthropomorphizing a non-existent person. Okay. Next, the physics system will also contain something we're going to call gravity 2D, and this will be a force generator, which basically creates gravity. And lastly, we'll have a float, which is our fixed update amount of time, because we want to update our physics with a fixed update so that it runs consistently across machines. This is very important, and we may take a look at this in a future tutorial, what happens if you don't have this fixed update, because it actually can mess up quite a few things. So, and when you create this physics system 2D, what you will want to take is just what the fixed update delta time will be, and you want to take in a vector 2f what the force of gravity is going to look like. That way, the users of this engine can customize these as they would like. And so we'll say force registry equals a new force registry. Just initialize everything down here. Then we will say rigid bodies equals new array list. And we will say gravity equals new gravity 2D, but we don't have that yet, so we'll wait on that. And fixed update is equal to fixed update delta time. And the reason I added the DT on here is just that the users of the engine know this is the delta time fixed update. Sorry, just a little bit more explicit, but inside of here we know it's the fixed update, so no point adding that DT there. Okay, and then this physics system is going to take in a float delta time for update. And you may be like, well, why do we need delta time if we're initializing it with how we want it to be? Well, that's because in our game world, ideally what we would have is 0.16, that's 1/60th of a second, so milliseconds for every frame. But in reality, what ends up happening is sometimes you'll have 0.17, 0.14, 0.2, and on it goes. So you're not going to get an ideal 1.16 milliseconds. And so to correct for this, what you do is you basically create an accumulator that says, okay, right now we need to update our physics just once this frame. But then all of a sudden, if your accumulator eventually gets to like 0.33 milliseconds, then that means that now all of a sudden you need to update your physics twice in one frame. Like say you hit a lag spike or something. In order to ensure that your physics is running at a consistent rate, what you would do is then you would say, okay, we actually need to update our physics twice with our fixed time because we're 3.33 milliseconds lagging. And we'll worry about that later. And once again, look at that in a future tutorial. For now, we're just going to have it as it is to make our lives easier. And then we're going to have a void fixed update, which does not take a delta time. And this we'll just call fixed update for now. We will use this delta time in the future to correct for that issue that I was talking about. Now, inside a fixed update, what we're going to do is just say force registry update forces, and we're going to give it the fixed update for delta time. And we're going to update the velocities of all rigid bodies. This is super exciting. This means we're actually going to do stuff, right? But we don't know how to do that yet, so we're going to wait on that just a moment. And the last thing we want to do is say public void add rigid body 2D body, and this will just say rigidbodies.add body register gravity, which we can't do right now, but we will do that in a minute. And yeah, we'll say body.init, which we don't have also, but we will have in just a moment. Now let's go into our rigid body because we're actually going to make quite a few additions in here. So first thing that we're going to do is we want to have a private float mass equals, we'll initialize it to that, and we'll say private float inverse mass equals 0.0f. We're keeping both because oftentimes you will want to deal with inverse mass rather than mass, but it's easier to look at mass if you are actually dealing with the variables, so we keep mass too. Now, we will need some getters and setters for the mass, so what we'll do is we'll just say create getter and setter for mass, and now we have the getter and setter. Cool, I actually remembered that shortcut. And when we set the mass, what we'll do also is we will just say if this.mass does not equal 0.0f, this.inverse mass equals 1.0f over this.mass. All right, so that is good. And doing this, we might actually not need this init method because I initially had that init method to do exactly this, but it makes more sense to do this when you're setting the mass. So yeah. That is why you use getters and setters, not public variables. Because if this had been public, then somebody could just change the mass willy-nilly somewhere else, and we would never know about it. And all of a sudden, inverse mass is completely inaccurate. So, setter means we can set it, and we know exactly what happens when it gets set. Now, for the real magic, this is going to be our public void physics update, which takes in a float delta time. This is where everything is going to happen that we were talking about, sort of how we sum up all the forces we get the resultant force, and then we update the acceleration, the velocity, and so on and so forth. In order to do that, we will need another variable up here too, and we'll call this private vector 2f force accumulator is what this is going to be. And we'll initialize this just to a new vector 2f. And the force accumulator is basically just going to be the sum of all the forces, right? So that's literally all that is. It will contain the resultant force by the time we hit physics update. So inside of physics update, first thing we'll do is we'll say if this dot mass equals 0.0f. You can't work with zero mass objects. They don't exist in real life. And so we will use zero mass objects to represent infinite mass objects, or things that don't move. Something like the ground would have a zero mass, which means it's infinite mass. Next, what we want to do is calculate the linear velocity. We'll delineate this even though we aren't actually using angular velocity yet, because we will in the future. And what we're going to do is we're going to say the acceleration is equal to, we're going to wrap this in a new vector 2f, the force accumulator, so the sum of the forces times the inverse mass. Remember, this is literally Newton's second law. The acceleration is equal to the sum of the forces times the inverse mass. That's pretty straightforward. And then we will say linear velocity dot add acceleration dot multiply dt. Remember, so linear velocity we said is equal to the change in position, or the change in acceleration over the change in time. Or if we're doing it frame to frame, we just add in the acceleration times delta time. So I said it was equals. Technically, it is equal plus. So it's like, okay, we're adding the acceleration times the delta time to get where we are at the next point in time. And then we'll do the same thing with the linear position. We will say this dot position dot add new vector 2f linear velocity dot multiply delta time. And you'll also notice something interesting here. We multiply delta time once again. And this is sort of just a phenomena that you will see in physics if you ever take it. When you integrate it using actual calculus, what you'll notice is position will have dt squared inside of the calculation of how to solve for it, which this sort of gives you that reason too. You're like, oh, I have to multiply by delta time twice, which means I end up getting dt squared. So if you ever take a physics course, you'll notice that, and this sort of just shows that in a much simpler fashion than actually using the calculus to solve for that. Next, what we want to do is sync the collision transforms, and we also want to clear our accumulators. So let's do the clear accumulators first, because that one is super simple. It's literally just public void clear accumulators, this dot force accumulator dot 0. So we just zero that out, clears it. Now public void sync collision transforms. This is going to be in charge of syncing our physics transform, because remember, we hold our own copy of the position and the rotation, but typically the game engine will have some transform that it is using, and we will use that right here since we are integrating this directly with our engine. We'll say the transform raw transform. And this will be the transform actually attached to the object. Now, you won't actually need to use this object, because we'll basically say inside here, if the raw transform does not equal null, then we'll update it. But if it is, then you don't have to worry about it. If the raw transform is not null, and if you have some transform you're using in your own game engine, this is where you would use that version. You would say raw transform dot set, or dot, in my case, dot position dot set this dot position. So basically, I'm just setting my transform to this guy's position, to the position that we have located in here. We're going to do all of our math on these values, but we want to make sure that we sync up at the end of every physics update the actual game object's position that we're using for rendering and stuff. So render transform, physics transform, we keep a copy. Now we will need just a couple more methods in here for ease of use, which is just public void add force method, and this will take in a vector to a force, and we'll just say this dot force accumulator dot add force. Very simple. So if we add a force to the object, then we literally just add that to the force accumulator, and because of D'Alembert's principle, by the time we get to the physics update, the force accumulator contains the sum of the forces, which is equal to the resultant force, which then gives us acceleration, because acceleration is just the sum of the forces times the inverse mass. All right, and that should be it for this. Now, we want to update the velocities, right? So how do we do that? We'll loop through inside of our physics system all of our rigid bodies. Oh, until I is less than rigid bodies dot size I plus plus. And then we'll say rigid bodies dot get I dot physics update, and we will give it the fixed update time. So 1/60th of a second. And we just update all them, which runs all that code we just wrote and updates the transform and everything for our things. Next, we need gravity. This will sort of showcase how we use these force generators now. So we'll make a new class, call this gravity 2D, and we will add that. And then I'm going to say this implements our force generator. So this is a force generator. And in order to do this, we need to implement the method update force, because that is the one method all force generators need. Now, if we want to create gravity, what we're going to say is we need to take in a vector 2f, the force, and this is just the force that you want gravity to have in your game world. And then up here, we'll say vector 2f gravity. So lots of gravity. All it is a force. And then inside here, we'll say this dot gravity dot set force. Now down inside of our update method, how does gravity actually work when you update it? Well, this is kind of fudging it a little bit because technically this isn't completely true, but we can think of gravity as just the force equals the mass times the acceleration. In actuality, it's a lot more complicated than that, but there's no reason to go into all that. So what we'll do is we'll just say body.add force. What force do we add? Well, we add the gravity, so we wrap this in a new vector 2a, just so that we don't actually change it, times delta time. No, times the body.get mass. And mass times acceleration. Gravity is an acceleration, right? That is what gravity is. So we just multiply that by mass, and we have our force. Nice. Now let's go back into our physics system. When we add a rigid body here, we want to register gravity. So we'll say this dot rigid bodies dot add, or no, I'm sorry. This dot force registry dot add, and then we want to add our body, and we want to add in gravity, which is up here, and it looks like it is auto imported that. And so right in here, we'll say gravity equals a new gravity 2D, which is a force generator, and we will take in the force that they give us. This is the acceleration due to gravity. Oh, and we should make sure that we say this dot gravity right here, because we do have this and this. So let's go ahead and just name this, add that here too, so that we know exactly what we're talking about. This dot gravity is new gravity 2D with the parameter gravity. Okay, and that should be it. Now we want to actually test this. If you have your own rendering capabilities and everything, use those now, but I will use what we have in here to test all this stuff. So I'm just going to go up here, and I'm going to hard code all this into our level editor scene. We're going to say physics system 2D. This is going to be our physics equals a new physics system 2D, and this takes in delta time, which we're going to say is 1/60th of a second is how long we would like it to last. And then we're going to take in gravity, which I will say is just 0 and minus 10. To approximate it. Gravity is 9.8 meters per second squared on Earth, so we'll just do -10. And then we're going to say transform object 1, object 2, and rigid body 2D, RB1 and RB2, just so that we have all those variables and we don't lose anything. Then right here, right before we load the resources and everything, we will literally just initialize all the variables that we want. So I'm going to say obj1 equals a new transform, new vector 2f, 100, 500, that's its position. I don't care about the scale. obj2 equals new transform, new vector 2f. We'll go 200, 500. Once again, I don't care about the scale. RB1 equals a new rigid body 2D. Duplicate that and just change this to 2. And then we're going to say RB1.set raw transform. Oh, and we don't have a setter for that. So let's go into rigid body real quick. Go up here to raw transform and say alt create setter. There we go. And that is nice. So that should work perfectly fine. Go back into level editor scene. Now RB1.set raw transform, and we will set that to obj1. So we're just going to give it the transform up here so that we have our syncing abilities. Duplicate that, change these to 2. Then we'll say RB1.set mass to 100. We'll duplicate that, set RB2's mass to 200. This will be interesting. Then we'll say physics.add rigid body RB1, duplicate that, RB2 2. So we add both rigid bodies, and then inside of our update method, we just want to make sure we draw and render, or update and draw them. So we'll say debug draw dot add box 2D, and we will add in obj's 1.position is where it's located. The dimensions, I'm just going to say, is new vector 2f 32 by 32. Duplicate that. We're also going to use obj2's position. And do we also need a color? Oh, we also need a rotation. So we'll give that a rotation. And while we're at it too, let's give it a color. We'll say new vector 3f100. Just make the first one red, and these don't matter. You can make whatever you want. And for the next one, I'm going to give it like a dark green. So I'll do 0.2f, 0.8f, and then like 0.1f. All right. So that's just giving it a color. You don't have to worry about that too much if you don't want to. You can just give it the default color, which is like green. And let's say physics.update, and we'll give it delta time. All right, let's run this and see what happens. Fingers crossed it all works, and we get a null pointer exception. Inside of here, we said this.gravity.setForce. We shouldn't be doing that because gravity is null. So what we should say is just this.gravity equals new vector 2f force. All right, and that should fix that. Let's run this again, see if it works. And I saw a blip, but it was very fast. So, did we do something wrong? I'm guessing we did. And you know what's happening is when we set the raw transform, we never actually sync them here. So what we should do is say this.position.set raw transform.position. This should fix that bug. Let's see if that works. Okay, yeah. So that was inside of rigid body 2D. We just need to make sure that we're setting the position when we set the raw transform, because otherwise the position is 0, 0. Anyways, this is working. This works. And another really interesting fact too, remember gravity, when it's acting on two objects of different masses, it doesn't matter. It will affect them the same way. And what we see here is that exact phenomena. And that's really cool because what this tells us is that we're modeling these physical forces correctly, because in real life, if you have a brick and a feather and you drop them off a building, they will hit the ground at the same time. Now, in actuality, that won't happen because of drag, but we're not modeling drag inside of our physics simulation here, so we won't see that happen. So just revel in the glory of this amazing 2D physics system that is working correctly. If you want, look at some other forces and try and model them using a force generator and see if you can get it to look like it would in real life. In the next episode, what we're going to do is we're going to actually model a spring force, just so that we can sort of see how this works in a little bit more detail. And that will be cool to see how to sort of implement this too, because then you can use this to implement literally buoyancy, drag, and whatever forces that you want to come up with, or whatever real life forces you want to simulate. And you can do that all through our force generator. Very powerful, and really like that concept, which is why I use it in here. But anyways, that is it for this tutorial. I will be releasing a game engine tutorial within the week, probably on Wednesday. So keep a lookout for that. It's just going to be conceptual though, and then next Saturday we will actually implement the game engine's concept. So keep an eye out for those, and I will see you guys in the next tutorial. Thanks for watching. I hope you enjoyed.